Hello friends, I am Prashant V Dhanshetti, Assistant Professor, Department of Civil Engineering from Walchand Institute of Technology, Solapur. Today I am here to give a brief introduction to moment distribution method of analysis. At the end of this session, the students will be able to understand fundamental principles of the moment distribution method. They will be able to identify and describe essential terminologies such as stiffness factor, distribution factor, carryover moment and fixed end moment, which are required for the moment distribution analysis. The moment distribution method is an iterative structural analysis technique used to solve statically indeterminate beams and frames. It was developed by Hardy Cross in 1930s and works by successively distributing and balancing moments at joints until the equilibrium is achieved. The method simplifies calculation by considering the stiffness of members and using distribution and carryover factor to distribute the moments. Now, what do we mean by determinant and indeterminate structure? Structure is generally classified into two categories as determinant structures and indeterminate or redundant structures. Determinant structures are analyzed just by using the basic equilibrium equations. By this analysis, the unknown reactions are found for the further determination of stresses. The basic equilibrium equations are summation of f of x is equals to 0, summation of f of y is equals to 0 and summation of m is equals to 0. Whereas the redundant or indeterminate structures are not capable of being analyzed by merely using equilibrium equations. Along with the basic equilibrium equations, we require some extra conditions. These are called as indeterminate structures. Now, the terminologies which are used for moment distribution method process are carryover moment. Now, what is carryover moment? When a moment m is applied at one end A. So, if you see this figure, a moment m is applied at end A of a member allowing rotation of that end. So, this is allowing rotation at that end, that is theta A, and fixing the far end. So, this is the far end, fixing the far end some moment m dash. So, this some moment means m dash develops at the far end B. This moment is called carryover moment. Carryover factor. The ratio of carryover moment to the applied moment is called carryover factor. So, that is equals to m dash upon m. Stiffness. Moment required to rotate an end by a unit angle, that is 1 radian, when rotation is permitted at that end, is called the stiffness of the beam. Now, if theta A is the rotation at the end A, now the stiffness of beam AB is equals to K, that is equals to m upon theta A. So, this m upon theta A will be the stiffness of this member AB. Distribution factor. When a moment m is applied to a rigid joint O, now here this is the rigid joint O and it is connected by various members, that is OA, OB, OC and OD members are connected here. The applied moment will be shared by the members meeting at that joint. So, when a moment m is applied at this rigid joint O, this moment will be shared by the members meeting at that joint. The ratio of the moment shared by a member to the applied moment at that joint is called the distribution factor of that member. Now, for example, if we see that MOA if MOA is the moment shared by this member OA, when a moment M is applied at this joint O, therefore, the distribution factor for OA member is equals to MOA upon M. Now, expression to find the distribution factor, let M be the moment applied at this rigid joint O. As the joint O is rigid, all the members will rotate by the same angle theta. Let M1, M2, M3, M4 be the moment shared by the members OA, OB, OC and OD respectively. Now, if we see this all moment shared by the members, if we take a summation, that will be equal to the total moment M applied at the joint. Let K1, K2, K3, K4 be the stiffness and L1, L2, L3, L4 be the lengths of the member OA, OB, OC and OD respectively. Now, theta is equals to M1 upon K1. As theta is equal for all the members, therefore, that will be again equal to M2 upon K2, that will be equals to M3 upon K3, that will be equals to M4 upon K4. Now, if we make a summation of all numerators divided by summation of all denominators, so what we will get? Theta is equals to M1 plus M2 plus M3 plus M4 divided by K1 plus K2 plus K3 plus K4. Now, we know that if we do the summation of all this moment shared by the members, that will be equals to total moment M divided by the K1, K2, K4 will be the stiffness of the members. So, that is again equals to summation of stiffness, that is Ki from member 1 to 4. But we know that Mi is equals to Ki into theta. Now, putting the value of theta, so theta here is equals to M upon summation of Ki. So, putting this value in this equation, what we will get? Mi is equals to Ki into bracket M upon summation of Ki, and I will be equals to 1 to 4, that is the number of members meeting at the joint. Thus, a moment which is applied at a joint is shared by the members meeting at the joint in proportion to their stiffness. Now, distribution factor is equals to Mi upon M. So, that is equals to, now Mi is equals to Ki upon summation of Ki. So, the distribution factor is equals to stiffness of the member divided by summation of all the stiffness of the member at that joint. Thus, the distribution of member, that is Ki upon summation of K, where summation is over various members meeting at the joint, and summation of K is called the joint stiffness, the member stiffness according to their end conditions. So, bending stiffness of a member, if the far end of the member is fixed. Now, if I see in this example OC, now from O to C, this C is the far end. So, if this far end is fixed, the stiffness will be 4 EI upon L, and if the far end is hinged, K is equals to 3 EI upon L. Similarly, the relative bending stiffness of a member, if the far end of the member is fixed, then K will be equals to I upon L. If the far member is hinged, K will be equals to 3I upon 4L. Now, the relationship between applied end moments M and the rotation theta, if the far end of the member is fixed, then the K is equals to 4 EI upon L into theta, and whereas if the far end of the member is hinged, K is equals to 3 EI upon L into theta. Now, we require the fixed end moments, and we have to distribute the fixed end moment according to their stiffness. So, we should know what will be the fixed end moments. The fixed end moment is the end resisting moment of a member induced over the fixed support. It is used to find out the variation of moments along the span of the member. Formula for fixed end moments will depend upon the many parameters like variation of load over the member and type of the support. If a fixed end member is having a point load at the center, therefore, MAB is equals to MBA is equals to PL upon 8 will be the fixed end moment. And if we have an eccentric load which is at a distance of A from end A and at a distance of B from end B, then MAB is equals to PB square A upon L and MBA is equals to PA square B upon L. If we are having a fixed end beam with UDL over the whole span, then MAB is equals to MBA is equals to WL square by 12. If we are having a uniformly varying load which is at an intensity of W at end A and 0 at end B, so MAB is equals to WL square upon 20, whereas MBA is equals to WL square by 30. So these are the references which I have referred. Thank you very much for watching my video.